Okay, so let's begin. What we're going to do with these series of lectures coming up, so the next 4 lectures, 4, 5, maybe even 6 lectures, are going to focus on building on the foundations that we've already established. So we're going to talk about different types of architectures that you've probably heard before, and start to sort of bring the discussion into more familiar sort of architectures. So we're going to talk about things like convolution today, and then this time next week I'm going to talk about transformers. Ferenz is going to talk about sequential models, and we're going to really sort of start to build our understanding of going from the fundamentals of deep learning into the more state-of-the-art methods, and just having discussion along the way. So today we're going to talk about convolutions. You're going to have questions answered for you, such as, well, why are they so good at images, for example? And instead of just explaining convolutions as a sort of in neural networks as a mechanism that's applied, I want to describe them as a set of design decisions that have been taken that extend beyond the fully connected networks we've seen already. So it's really exciting. It's going to be fun. So I'm going to start by reminding us, taking a little detour into inductive bias and what it means for machine learning in general. And then we're going to explore what it means for neural networks. And so what is that inductive bias? I think you've heard Ferenz mention this already, just in passing in a few lectures. Essentially, it's the act of embedding some part of external knowledge into the design of the model. And so it happens all the time. It's very useful when you don't have enough data. And so you need to start to impart some other knowledge. So it could be from a domain-specific source. So for example, in the health domain, it could be a doctor who understands the phenomena and wants to embed that sort of knowledge inside the model itself, as well as the data. Other times you might be you might be modeling things that are related to sort of physical phenomena. So you want to embed like the laws of physics and so forth into that model. And so let's start with a very simple example, just to kind of make sure that we're all on the same page. Imagine that we have 2 data points. We're doing a predictive task, and we have a reason to know that the sort of model we're trying to fit fits this equation that you're seeing up here. Now, to make progress in designing this model so that you can do a nice prediction, you have to introduce either more data or some sort of external knowledge. And so let me just draw a couple of examples here. Where's my cursor? 4, 5. And so imagine if I have some other external knowledge, which leads me to believe that, this is going to work. Oh, sweet. Yeah, so imagine if I have some reason to know that these parameters in my model are all going to hold to be the same, and they're all going to be 0. And that quickly allows me, even using the 2 data points that I have, to know that the predictive model is going to look something like this. And so that, in a nutshell, is what an inductive bias buys us in the design of models. So you might be asking yourself, oh, how does this map to neural networks? Well, let's revisit the design of neural networks that we know thus far. And so if I just turn this off, clear. And advance one more. Oops. Yeah, so far, we've only seen neural networks of one kind, these fully connected networks. And so that's what's being illustrated here. Now, these type of networks actually have very little inductive bias in comparison to the ones we're going to be looking at moving forward in today's lecture and other ones that come subsequently. If you look at the design of them, they, for example, have very little assumptions built into them about how we're going to treat the input data, for example. And in fact, there's a well-known result called the universal approximation theorem, which says that as you extend the number of neurons in the hidden layer, this hidden layer here, as you extend them arbitrarily to arbitrary sizes, you can approximate with this structure any function that you like. And so these are very flexible designs of neural networks. What we're going to talk about today is how we can move from this very flexible design and impose some, what I would, at least in my mind, I would say design considerations for what we're trying to model, or in the language of machine learning, inductive bias, into these type of very flexible architectures so that they can do very easily certain types of tasks. And so we're going to be talking about convolutional neural networks. They're famous for dealing with images. but they actually have more generic properties baked into them, which make them very well suited to modeling all sorts of other tasks too, not just image, although that's what they're probably most famous for, being able to do very well. And we'll talk about some of these applications in the later part of the lecture. So to talk about these sort of design considerations and how you might want to change the design of how this neural network functions, let's just imagine we're going to stick with the task of image, and that you're going to provide as input to the model some image, some picture, right? And so I don't know how well this is going to work, but just imagine you have this this dice here, and that your sort of field of view that you see right now wants to be able to recognize this dice as a dice. And then for the model to work well, there's some certain properties that we want to have this model to have. So for example, if I move this dice through your field of view, even though it's changing position inside your input, even that's changing, the concept of dice still needs to hold. The model still needs to recognize the same thing, except that the input the model has is obviously changing, right? So if you imagine what the model would see, it's going to see some representation of the image reduced down to some digits, right? And then as I move this around, those digits are changing. But what we want to have is what's known as translation invariance, right? Doesn't matter where I sort of translate this object, the model needs to still output the recognition of dice. There's a bunch of other types of properties that will also be useful, things like rotational invariance and so forth, that you can also impart inside the model design. But what we're going to sort of focus on in the discussion is the ability of CNNs, convolutional neural networks, to be very good, very quick at designing and recognizing, very quick at training a model that is has properties like translation invariance, and also is very fast to understand spatial connections, which are also very important if you're trying to sort of understand the visual domain for obvious reasons. Just before we advance, one thing to note is that because this is a fully connected network, there's any piece of the input can be connected to anything else, right? But whereas we're going to quickly see, by constraining the design of the neural networks, we actually want to have different parts of the image or the input quickly understand that there's local structure that it wants to learn. But more on that as we progress. Before I move forward, I just want to also point out that inductive bias can also be seen more generally, even in the networks we've seen so far. So we're largely going to be talking today about modifications you can do to the neural network architecture, because that is one of the most common ways that you insert inductive bias or design into a neural network. But just generally speaking, the networks we've seen, or the style of modeling itself, already has inductive bias baked into it. So here, there's a couple of common things that you might not have realized are kind of already imposed inside the design. So for example, we already have made a decision that the style of models that we want to find should be easily trained through gradient descent methods. It's obvious that it's a bias that we've put into the modeling design space as we move forward. And there's a few other ones listed there too. But that's just to kind of indicate that it's not only about architectures, it's about a bunch of other sort of design decisions that you might make. Okay, so that's a bit of a background. Let's move on to talking specifically about convolutional neural networks, and we're going to enter this discussion by talking about the sort of the key operator, the key sort of operation that these networks have, and then through the discussion of them, we'll tie this back to this inductive bias of discussion. Okay, and so then if that dice example was a bit sort of abstract for you, I thought I might give it a try to kind of liven the lecture up. This is an animation that gets across this notion perhaps maybe a bit more clearly. What you see here on the left-hand side, we're just imagining that we want to develop a convolutional network that I was saying that we want to have these nice properties in this design of the architecture that allows it to easily and promotes the development of models that have certain properties. And here we have this translation invariance property being shown to you. On the left-hand side, we have the input that's given. In any sort of computer vision task, the input is just going to have some correspondence between I see the view, and there's some translation into a series of pixels, where colors are sort of mapped in some sort of spectrum of values. And then what we want to, so as the objects move and translate and so forth, the input is going to change quite dramatically. And we want to have the model to be robust and able to realize that these sort of changes are not significant, are basically noise in the sense of being able of affecting its output. And so this is what we see here. We see two versions of we have this animation here that is showing us two different types of models. On the top, on the top model, we have a translation invariant model. And so you'll see this 3 moving around the input space. And then no matter where in the field of view the 3 moves, you'll see the output of the model, it's labeled logits, you'll see it's not changing at all. And see below, we see a model that has does not have this property. And so as the 3 moves around, it's changing its decision about what this thing could be. Okay, so we want to have a model, we want to have a design of a neural network that, that has this type of property and many others. So the core way that we provide this is through this convolution operator. And so let me explain this key part of the model. There's a new set of learnable parameters. So we don't have these weights that we learn that connect the different nodes together. Instead, we have what was called a kernel, or most often also called a filter. And that's highlighted in blue in the middle there. And in this particular example that I'm showing you, we have a kernel size of 3 by 3. And so those parameters inside the kernel are all learnt by the optimization process. That's going to decide what should I set these values to be such that I'm going to have very good accuracy as I train over many, many examples, right? In this example, to see how it operates, the input here is this 5 by 5 input. And then we can go through the equation at the end, but the basic principle is being shown on the right-hand side, whereby in the input that's provided to the network, maybe I should draw. Yeah, okay, let me just draw this. Yeah, so then we have, it's basically, there's an animation that's looping around, but if you pay attention to, say, this portion, in case it's not obvious, what happens is that at the starting point of the operation, the kernel is indexed to the 0th point in the input, and it is then moved around. At each position that the kernel is placed over the input, it does an element-wise multiplication between the kernel parameters and the input. And then a sum is performed over these element-wise multiplications, and that populates the output. So this guy here is what is produced by this single convolution operation inside a network and passed on to the next layer. And then inside every layer, you can have more and more of these kernels. You don't have, this is just one example of a layer that has one kernel, but you can have many of them doing different types of transformations. So another way to think about this is that this is a learned transformation of a certain kind from the data input, or it could be from the earlier layer to it. And so right now we're looking at a sort of zoomed in aspect of probably the key operation. And the equation above us here just spells out what I just said. So it's telling us for any sort of arbitrary point in the output matrix or tensor, and for the ith, jth position, it's going to be a bias term that we're going to see in the next couple of slides. So just a learned bias term, so a scalar value. And then we see that we have this wxy, so that is an individual element of the kernel, and these sum values are indicating that we're going to sum across all these values when the kernel is moved around. And so this is the basic starting point of seeing what the core operation of a convolutional network is. And what's very cool is in about 4 slides time, we're going to see that although this cooperation looks quite different to the style of neural architectures we've seen before, it is actually just a special case, like a special case of the fully connected network, a case where you have constrained the fully connected network's very extreme open wide behavior to a very specific type of behavior that provides this type of transformation. So it's really interesting too. So let's move forward to, oops. So that's the core concept. Let's start building on this core concept to understand the sort of full story of these convolutional networks. The next part of the story is that there are two other types of behavior that it needs. One is step size. So you'll notice that in the first animation, the kernel was moving across the input space by a unit of one element. Now that's a parameter that can be set. And so these animations here are showing step sizes of different sizes. So you can have a step size of 1, step size of 2, or whatever seems to work well for your data. The way to understand these diagrams here, if it's not clear, is that if we think of the last thing as a learned transformation between the input and the output, this diagram that we see, I should just draw. This diagram here is showing us the output. This is the input, and these lines here are showing us the transformation that's gone from input to output that we saw before. If you can see, there's a slight discoloration between the input on the input moving around, and that's the kernel that we see being sort of applied to the input, right? And so in this first animation here, we have a step size still of 1. So we could say step equals, 1. But you'll notice on the middle animation, we have now a step size of 2. And on the final animation, you might see something a little unusual happening. We still have a step size of 1, but a new concept is introduced, and this is the concept of padding. And so you can define these operations to also having a padding size that defines an apron that exists around the edge of the input. And that sometimes can be necessary to kind of capture information that's at the edges of the input. So you can see here, we have a padding of 1 that is surrounding the actual input, and that enables the kernel to be applied slightly off center. So it's, I guess, -1 position and then moved around. Okay. This equation here, I decided to include it because sometimes it can be, just to allow you to understand what the dimension translations are from input to output. This equation here is interpreted by in one dimension at a time, and it allows you to understand that if you have a certain input size and then a parameterization of the convolution operation, what is the output size going to be, right? Because so for example, you'll notice here the output is much larger, and that's because we have a padding. So therefore we have sort of like a virtual increased input size. And so if you want to work out what the output is going to be based on how you parameterize the convolution operation, then this equation can give it to you. Although if you think about it, you can find this, you can kind of derive it yourself from how it's going to behave. Yeah, those are the main points. Great. So now this gets really interesting. What I next want to explain, it just give you an intuitive understanding, although this diagram is accurate in terms of all its colors and everything, but I want to give you an intuitive understanding between how what I've described so far can actually correspond to a fully connected network. And so let's take a little time to work through the diagram. Left-hand side, we have the same animation that we saw before, so you can interpret it the same way. Nothing new is there. We just have our input, we have this kernel moving around or filter. You can sort of take your pick of terms, and we have this output. And so the transformation that's applied here corresponds to a fully connected network as described on the right, that I just circled in red. And to define a fully connected network that has the same transformation, the first thing you need to do is you take your input. So this is what we're seeing here. This is an input that's going to be provided to this special constrained fully connected network. And then the first thing you need to do is you need to linearize out the values of this 2D input, right? So we go, there's many different ways you could decide to linearize out this input, but this is, so what we've done is done the most simple type of linearization, where you just start at the 0th element, and then you just map that to be the value of the very first input neuron, and then you just go left to right, row by row until the end. And so then if you look at this input, this 2D input that we normally provide to our CNN, we've now provided it to this fully connected network, and you can see the colors corresponding top to bottom. They're the same values that you see in this 2D input. Is that clear so far? Okay. And then what's the in this particular fully connected network, the hidden layer, this next layer here has only got 4 neurons, right? And then each of these neurons is going to correspond to values of this output space, this in the transformation. So then you could, if we just call this like 1 to 4, this is just the same thing as saying 1 to 4 here, right? And then all we need is a special type of restriction on the fully connected network that would allow the same type of translation to occur, this transformation to occur from layer to layer. And so what it turns out that you need to do is 2 concepts that you see being sort of shown here. One is that for many of the potential weights between this layer and the next, that normally when a fully connected network could be assigned to any value, right? So this is what's being shown by these little dotted lines. And normally these could be anything, right? Because the network is fully connected. So each node here has a connection to every other node in the prior layer. But for it to have the property of this convolutional network, many of these potential links have to be set to 0. And then the final step is that we need to group a remaining set of links, force them to be the exact same value. And this is a concept called weight sharing. So that's why this term here, weight sharing, has come up. Let me just remove the diagram, the little drawings, to show a couple of other things, so we can see what I'm saying a bit more clearly. Yeah. And so then if we just look at these lines here, each of these, if we look at these lines, they're colored. And then if we look at these values here, they're also colored with X. The colors denote a weight value, and they correspond to what's the weight assigned to this particular part of the input space. And then what you see is that many of these remaining weights have the exact same value. And so for example, these links here have the exact same value. These ones here have the exact same, I should have used a different symbol, maybe this guy. These have the exact same value. And so the final step in creating a fully connected network that has the same behavior as described so far is tying these weights to the same set of values. And so the exact same value, the exact values required to identically perform this transformation here depend on the values of the kernel. Right, so if the kernel here that you see moved around has some different parameters, well, these weight values have to be changed to a particular set of values. But if you do these things end up being equivalent. And so in that sense, a convolutional neural network, although as you describe it more naturally, as we easily describe sort of the algorithm, might look very different to a fully connected network. In fact, it's just a special case of it. So it's pretty cool. Let's see. Oops. Okay. Now there's one final level of detail I want to introduce in describing how these networks behave, and that is yeah. And this is, primarily, I want to talk about the fact that you can have multiple channels. And so a very natural way to think about this is in the case of application to image. But again, at the end, I'll mention a few examples where this notion of channel or having different sort of layers of information within the kind of space that you're modeling can also apply. But let's just stick to this example of image because it's very intuitive. To describe a complete visual situation, we often don't want to have just one dimension, but we have commonly three. And these are described as RGB, right? And it's from these pixel values, when you combine them, you can have this sort of fairly rich color spectrum. And so a CNN or a convolutional network often is parameterized to have more than one channel, and often three for the reason I just gave. And all this is that instead of having the input being a flat 2D tensor, it actually starts to having depth. And so then what I'm illustrating here is a complete example where we can see multiple channels existing. And so the way to understand this is that this input volume here, this is channel 1, so let's see, channel 1, 2, and 3. And then you can imagine this as a three-dimensional tensor that acts as the input. And because it's now 3D, our kernels that we apply to the input, they need to be 3D too. And remember, this is just a parameter. We could have ND, right? You can have as many dimensions as appropriate for your data. You could have, you know, if you had different, what's the word? Different parts of the spectrum of light, right? You could have more of those. Or if we're dealing later on, we're going to talk about how you can, very briefly, but we're going to show that CNNs have turned out to be very applicable to things like graphs. And then because they can apply to graphs, anything you can model as a graph, you could then also run through a CNN. You can use a CNN on speech. You can, there's many different things that you essentially that you might want to sort of apply a CNN to, because some of the properties of a CNN might be useful in different types of domains. But anyway, back to this. So then we have two kernels here. So yes, let me just focus on this kernel here. We've only talked about one kernel so far. You'll see now that our kernel needs to have three levels to it, and each of these slices of the kernel attend to one of the slices of the input, right? So then this slice here is going to be applied to this first or zeroth channel, and so on and so forth. Now each pairing of filter or kernel to each kernel or filter will correspond to a single channel of the output. So these values here that we used to see being decided by just one pairing of input channel to kernel 2D values are now actually populated by the sum by doing element-wise multiplication between each pair of filter and channel. So this guy 1 to 1, 2 to 2, 3 to 3, and then also this bias term. So you do element-wise multiplication across this these different slices of the kernel, and then you just sum them all up as including this bias value, and that becomes one element of the output volume. Is that clear enough? Yeah. Let me just clear this diagram off again, and I just want to make sure that we see another feature of this more complete example, and that's that we have an example of having more than one filter. Within a layer, you can have as many filters as you want, and so what's happened here is that in this this other yeah, this other part of the diagram, we see a new filter being introduced. So the output of this filter being applied to the input is going to be populated into this second dimension of the output. And so then this can either be at the very start of the input, at the start of the network, so it's applied to the raw input as it comes in, or it can happen at any point inside the network as we stack these layers on top of each other. Okay, so now you've seen essentially that's it. That is a convolutional neural network in its sort of core form. There's extensions of it that we're going to talk about in the later part of this lecture, but this is the heart of how these networks behave. Before we go on to these extensions that are basically kind of, we'll reuse these concepts. So you kind of know everything so far that you need to sort of know. I want to show you a code example that hopefully can do two things, maybe make this a little bit clearer. And also I want to show you this, this element of handcrafted features or transformations and learnt features that are now used in neural networks. So let's transition to a code example. This is just a Colab. Let's see, how do I can do this. Let me first clear the screen. And then I'll close this guy. Okay, so let's move on to the code example. I realized that we haven't put the collabs up from the last lecture I gave, but I'll put them in the Reddit channel so you guys can access them, and I'll do the same thing for this one so you can have a much faster access. We haven't quite got them onto the website yet, but that's just to say if you see this and you're like, oh, I want to play with this quite soon, you can do that. Let's see, we've got 10 minutes. Okay, it's just 10 minutes. The first part I won't really go into. It's you can navigate it by this table of contents that I set up. In the basic setup, there's nothing fancy here. We just have some helper functions that's loading this single image that we're going to play with as an example as we go through it. One interesting thing is this convolve function that is defined. And so you'll see in the code that this filter function is doing the element-wise multiplication between these two matrices. So really nothing fancy going on here. And then you'll see the result is just being summed, as I was saying, right? You do the element-wise and then you sum it together, right? And then you'll see the input to this is the image. And so this is this image that we see here. And then the kernel that's provided it. So there'll be some defined set of parameters that we're going to put into this function and it's going to do its work. And it's nothing fancy here going on. You see image, and you'll see here the different channels, 0, 1, and 2, right? Going through the different channels of this image. And then you'll see that this kernel also has a corresponding set of parameters for each channel. Nothing else here is, then we have some helper functions about showing both the kernels that are applied and then showing the output of the image, this output thing I've been talking about. So let's go through handcrafted features. So I've been, yeah? Can you increase the text size? Oh, sure, I can see if I can. I'm sure you can. Oh, yeah. Good, thank you for asking. Cool. So we're first going to talk about kernels being applied to an image that were built by humans, right? So humans have been interested in doing things like computer vision for a long time. Prior to deep learning, there was a huge amount of investment in thinking very carefully about manually designed transformations, or you probably have heard this word feature, that is able to extract information that is then able to be useful in doing discriminative tasks, as an example, right? So then some sort of transformation that allows us to build up a set of pieces of information that collectively tell us, for example, what object is it. And so the name of the game for a long time, as Neil was saying in lecture 1, we were very interested and excited about SVMs, and they relied very heavily on handcrafted features to work. So in a sense, there was a heavy inductive bias of humans coming up with what features are going to be useful, putting inside an SVM, and that worked really well, certainly much better than anything else we had for a long time, until we started moving to deep learning, which allows us to use the optimization processes that Ferenc has been telling us about to learn from the data what these transformations should be to provide good levels of accuracy. So that's quite a change. But let me just start off by talking about a couple of these hand-built translations. So then I'm talking about essentially two different kinds. One called Laplacian. I mean, the details of this, they all have history and have reasons why they work and so forth, but that part isn't that important to us. It's just the fact that these are two different classes of transformation that were developed over time, of which there's many of them. These ones are actually not the most complicated ones, but I use them because they're kind of nice and easy to sort of digest in this conversation. And then you can see them here. For this Laplacian style, we define the parameters of this kernel that you've been seeing before, right? This is a 3 by 3, and then it can be visualized like this. And so this is a 3 by 3 kernel that is then applied to this input image that we saw before. Yeah, this guy, and you'll see that, relatively, the comparative sizes of them are quite different, right? So then this thing is a 350 by, I don't know, 500 image. And so then we have a 3 by 3 kernel, so quite small, and it's going to be kind of moved around the image to come up with a transformation that we hope is going to be useful in figuring out what this thing is if the application is classification. And so we see from this Laplacian that what this transformation does for us is what is often referred to as edge detection. So there's many different types of transformations you could do that extract useful pieces of information. But one very common one in the domain of vision is detecting edges. Because if I can see an image and then, of course, the computer doesn't know what the edges are. To us, it's very natural where the edges of a dice or the edges of an object are. But the computer needs to have some way of knowing where edges are. We've discovered over time that it's useful for a computer to know where the edges are if it's going to just know what object it is, for obvious reasons, like the shape matters. And so here we have a transformation that does a pretty good job of removing different elements of the image that might not matter. So like the color of a boat might not affect whether it's a boat or not. And so now that's gone, and then we see edges of a boat that maybe are quite universal. So that, well, this particular kind of boat at least. So that's what happens when we apply the Laplacian. Let's move down, and we can see another type of okay, and then the reason I put this other kernel in there was that I just wanted to show that the actual values don't matter. It's the relative values between them. So here we have if you compare the two kernels, all I've done is I've inverted the values. So you can see this red is high. Blue is very low, white is at 0, and then I just inverted the value. So now what was low is high, and then you can see that what was high is now just inverted, and then the same output can be produced, right? So it's the relative values that matter, and there's a reason for this when we go down a bit further in the notebook. So essentially, as you go through it, you see, okay, there's other types of transformations. Here are these things called Sorel. There's a vertical version, and then there's quite a lot more interesting diagonal version. And again, these guys are all doing a specific type of information extraction called edge detection. You can see that they're doing it quite well. And the point here is, remember, these were designed by people, right? The idea of this. So let's now look at the type of transformations that you can see being learned within a neural network. So we've talked about neural networks like AlexNet. You've heard about these things like MobileNet, probably from other types of sources. And so these are networks used in practice, trained on thousands and thousands of images. And we're still in the kind of showing examples of applying hand-based ones. Let's start off with AlexNet, and then at any layer of any of these sort of real non-toy architectures, you're not going to find a couple of kernels. You're going to find many kernels. And so I chose a particular layer, the third convolutional kernel layer of AlexNet. And then what's interesting is that you can see learned transformations that have, they're obviously not the same as the manual design ones, but they have some similar structural patterns, which is kind of cool, right? You see the machine learning, at least within the collection of transformations it learns to do its job, we see some echoes of some of the ones that we've developed by hand. So you can see, for example, this is a real kernel learnt by the AlexNet. It's one of them at least. And then the way to read this is that these are the different channels. So there's 3 channels being used. So this is each of them. And so then, yeah, so if you look at these learned kernels, you can see that there is a high and a low, and then a bit of a if you, I'm not sure what the values. I'm not sure which way the notation is, but let's call this high, low, high, and then with these sort of 0 values, breaking them up. And this is very similar to this type of concept. Obviously, the human-based concept is a bit cleaner because we have to kind of operate we have to kind of reason about what we think may or may not work. This thing is just learning from the data just to find out what's working. The other point I want to make is I don't want to give the impression that the machine is having to learn the way that humans do it. It's able to train a wide variety of kernels of different kinds, and it's the composite of these different kernels that it learns that perform discriminative transformations from one layer to the next. It discovers, what works, what doesn't, and it doesn't have to sort of reason about it in the same way that humans do. And so as a consequence, you see some kernels, it's very hard to understand why it would be useful in terms of why it's doing that. And others, you can see pieces of information, types of transformations that do make sense. So for example, here we have one that looks quite similar to this diagonal Sobel, but here, for example, there's no, it's very hard to interpret why it decided to do that. You know that it's done it just from the optimization process. It found that this combination works well for the loss. And then you can move down and you can see the different, these are the outputs of different channels. So, so this is the first channel, second, third, fourth, fifth. And so just to be clear, it's not trying to find one single transformation at each layer. It's going to have a stack of them based on all the channels, and then collectively that's information that is passed on to the next layer. And that's what we see happening here. And so it's pretty cool that there are some parts of this transformation that's doing similar work to an edge detection. Okay, so let me move on to the slides, but you can have a play around with this. You've seen the MobileNet example, for example, but both AlexNet and MobileNet are much more complete non-toy architectures where we can see this behavior happening. Let's go back to this. Oops, how it is. Okay, so this is a summary. I'll probably move fast. I just want to make sure I get through the rest of the slides to give you the different concepts, but this is just basically summarizing the core concepts we've seen so far. And so in the remaining time, what I want to do is just run through extensions of this to kind of give you a fuller picture of what's going on. There are other kinds of convolution-based transformations that do not require parameters. So they're parameter-free different types of convolutions. And so most often these are used to do what's called pooling. And so what they're doing is that they're aggregating information. And sometimes they'll be used because perhaps the network, they might be used for a couple of different reasons. One reason might be that the network is too large and you want to kind of reduce some of the parameters so that it trains well. For example, you might want to, at some level of the architecture's set of layers, start to aggregate information together because you find that the information you have at that layer doesn't need to be shown at this resolution. You can still do well by aggregating it together. Other times you'll apply this layer just because it makes sense. Like you've got a bunch of information about a certain part of the image, and you decide that I'm going to put this layer in there to aggregate it all together, because just conceptually is what you want to do. So that's one thing. The transformation that's being shown here is so the input is this big image, the output is this second image, and the behavior of this is really simple. You have different kinds of operators that are listed here, max, min, average, and then what it does is these are parameter free, so you don't have these kernels with different parameters that need to be learned. You just have an operation that's applied. And so, for example, oops, let me get this guy. Yeah, so for example, yeah, you can see here, you might have a 2x2 max pooling layer applied to the input. And so it just finds the max value that's within all the elements that the kernel is looking at. So here the 6 is the largest value, so that's what happens in the output. So a very, very simple way of aggregating in different ways, right? What's the max? What's the min? To kind of digest information. Okay. Next, I just talked about AlexNet in the code example, right? So I want to make sure that we had a sort of view of this for a couple of reasons. One was I want to make it clear that in non-toy architectures, we stack these things together. We also stack these things together based on different parameterizations. And so what is quite neat, this is the, I recall that Neil referred to this paper in his very first lecture. He talked about quite a well-known paper, 2012, by Hinton and a couple other authors, also equally kind of influential. And so what is neat is that we can now, this diagram you see at the bottom is taken straight from the paper. And so from the information that we have from the prior lectures and this one, we can actually read this architecture and understand what it's doing. So yeah, again, if I just, oops, bring up this guy. This is the diagram. Here we have the input being applied. You'll note here that we have 11 by 11 kernels being applied to the input. It then progresses to the next layer. You'll see that in the next layer, we have 5 by 5 kernels being applied. That's what this is being shown here, 5 by 5. And then it goes on to, then it's, the output of that is provided to the next layer, where we have 3 by 3 kernels being built, and so on and so forth. And so you can see the sort of stacking effect of the network. And all of these, if I'm not mistaken, the first section of the network is a collection of convolutional layers that we've discussed so far, and pooling layers. So for example, you see this max pooling layer happening here and here. So for the design the architecture in this way. And at the end, we have fully connected layers being used. And the very last tensor you see, I've drawn over it, but actually it's one that is 1 by 1,000. And the reason for that is that there's 1,000 different classes to be recognized. And so at the end of this chain, all of these different types of components in this network, it's going to arrive at values that you can use to interpret which class the input belongs to. So it's quite, I think it's quite neat that you now can read a paper's diagram, a very famous paper's diagram, and you understand all the concepts in there. There's nothing there that you don't understand. Fully connected, you understand. Pooling, you understand. Convolution, you understand. So it's pretty cool. Yeah. I won't be able to go into the same level of depth, but I wanted to just show that there are different kinds of inductive bias that people have designed in the space of convolutions and then applied them to invent slight variations on the idea that we've come up with already. And often these ideas are to help model some aspect of the data, but at other times it's used because we realize that some of the flexibility, even though the convolutional layer is a constrained form of the fully connected, some of the flexibility of the convolutional layers are actually unneeded for some of the modeling tasks that we want to do. And so because it's more flexible than we need, if we further constrain it, we find that it can still do the tasks that we want, and perhaps it's faster to train, or it's more practical to use. And so there's a well-known idea called depth-wise convolutions that are one of the building blocks of MobileNet, which is the last architecture I had in the code example, which is why I wanted to describe this idea. This is an illustrative idea of which there are many, but I want to give you one example because MobileNet's in the code example. And the idea here is that on the left-hand side, I still drawing? Oh, crap. Oops. Yeah, great. On the left-hand side, we see the ideas we've talked about already. And so I labeled them vanilla convolutions. You can break down what they're doing, what these convolution kernels are doing when they process the input into two main roles. The first role is that they are aggregating spatial information as they move across the input. So then that's what the matrix multiplication, element-wise matrix multiplication is actually doing. So it's aggregating the spatial information across a very localized area of the input and moving across the front, right? So that's stage one. I'm aggregating spatial information. Stage two is that I'm just going to summarize across the channels. That's what the sum is doing. So a way to think about, so again, I'm just explaining a way that you can interpret what convolutions are doing. And the reason I'm doing that is that people thought about what this action is, and they decided that the flexibility being given to the kernels is too much. So they've came up with what's called depth-wise convolutional kernels, and they work as follows. Here we have here we have the input. Here we have a regular kernel. We break this kernel into three different. We break it into different tensors that correspond to different channels, and then every time we want to generate an additional kernel, we reuse the same spatial transformations time and time again. So earlier I'd said the vanilla kernels do two things. They do spatial aggregation and then channel-wise aggregation. In this depth-wise convolution, the idea is that we will reuse the spatial process across all kernels we want. And that's what's being illustrated here. And then we're just going to summarize across the channels differently for each kernel. And that's what's being illustrated here. So then it doesn't matter how many kernels you want to build into your layer. The first step is going to be reused, and we're just going to weight the spatial information differently and generate different kernels from that process. And so this is an extension of the idea that constrains the degree of freedom of the model even further, so that you can have a much more efficient model that turns out to still be nearly as accurate for a huge reduction in the cost of the models operating. So let me just end with two thoughts. One, I want to show you just how cheap this process is. Let me just clear this. And so highlighted in red are, these are the layers inside a MobileNet, and to form these new types of convolutions, the implementation is that you just have two separate layers. The first is doing this spatial step. The next is doing this channel-wise step. And then because you form convolutions from these two layer types, you can see that the number of multi-adds and the number of parameters required to describe the network is vastly lower. So, a network of the same size described with full convolution layers would require 29.3 million parameters, but then describing it in this very much constrained manner that I sort of quickly went through, drops it all the way down to 4.2. Now you'd think that reducing this sort of capacity or degree of freedom would drop down the accuracy, but it turns out that the accuracy declines, arguably a negligible amount, from 71 to 76 on this particular type of data set. So that you can see this as just yet another type of inductive bias that's being applied towards designing a network that operates in the way that we want. I know we're running a lot of time, so I just want to end by just reminding us that these convolutional networks are able to do far more than just classifying images alone. And so if we think outside the box of just classification to other types of tasks, they are applied to doing things such as a task called super resolution, where you increase the resolution of the image. So this is more a regression task, but they're even one step beyond an alternative from classification to a more of a generative type of application. They can even apply to completely different types of data. And so I mentioned earlier, they can be applied to graphs. So there's a variation of convolutional networks that can be applied to graphs. And so today you might have heard about these types of models being done for drug prediction, drug discovery, simulating physical models. If you look inside the architecture of these types of models, often you'll find convolutional layers there. And because you can map these type of data into something like a graph, and then you can use convolutional networks to consume and model that data as well. So the application of these things is much richer than the image ones that we talked about, because they have quite generic properties of sort of spatial locality and being able to represent across channels and all these different things that have much wider application than just image alone, although image is definitely what they're most well known for. With that, I'll end the lecture right on time, and if you have time, stay and you can ask me questions, but thanks for coming.